Hello, everyone. Good morning. Today we continue with vector valued functions and functions of several variables. So in previous courses like Calc 1 and Calc 2, we got to know the functions f from R to R, which means both the domain and the target or the codomain is something one-dimensional. For example, we had examples like y equals f of x equals x. Here, the domain is just x, is just a number. And the result is just another number. Or if you, for example, look at consider another example. For example, consider y equals f of x equals sine of x. Here again, the domain is where x is coming from, which is just a number. Again, x is supposed to be a real number. And y, the result, is also a real number. So in another sense, we can think about function as something which takes an input here we showed input with x. Then the function f does something to it. And then we got an output. Which we showed output with y. In previous examples, x was just a number. So it was something in R, set of real numbers. Set of real numbers, it contains all rational and irrational numbers. And the output was also something in R. Now we are interested in examples where our functions are either defined on R, the domain is still a number, but the codomain or target is something higher dimensional, like R2. Or codomain is something three-dimensional, like f is a function which is defined on R, but the target is R3. So for example, the example of the first one is a function which takes, again, a number, because note that the domain is still something one-dimensional, but the target or codomain is something two-dimensional. So f of x is not just a number, is a vector. For example, the first component can be something like x squared plus 2. The second component can be something like sine of x. In the second example, it's similar. The domain is something, again, one-dimensional. So f takes only a value, a number, but the result, the codomain, is something three-dimensional. So f of x is a vector, but in R3, it has three components. So say the first component is x plus 1, the second component is x squared, the third component is 2 over x. These are examples of functions of several variable, vector valued functions. The reason is that if you look at the function, it's a vector in R2. So it's a vector in R2. That's why we call it vector valued functions. Here, the result is a vector in R3. So for example, if f is a function from R to R2, like f of x equals, it should have two components. So for example, consider this one. The value of function at each point is a vector. For example, f of 1 is 1 squared plus 2 and 2 over 1 plus 1, which is 3 and 1. As you can see, 3 and 1 is a vector in R2. So this function, this function f, its domain is R, its target is R2. This function sends every point in R to a vector in R2. For example, it sends 1 to this vector 3 and 1. For example, it sends 0 to f of 0. What is f of 0? It's 0 squared plus 2, 2 over 0 plus 1. What is that? 2 over 1, which is just 2. So it sends 0 to 2 and 2. So this function sends 0 to this vector, sends 1 to this other vector. So you see, this function sends numbers. F is a function which sends numbers to vectors. This is what we call a vector valued function. Let's look at another example. Suppose f of x is x plus 1, 2x, and x squared over 2. Now here, it's a function which sends r. As you can see, the domain, it's just a number. The target is R3. There are 3 components here. So f, its domain is just R. Its target is 3-dimensional space. So for example, f of 0 is 0 plus 1, which is 1, 2 times 0, and 0. So for example, 0 goes to this vector. It sends 0 to that vector. What is f of 1? F of 1 is 1 plus 1, 2 times 1, and 1 over 2. So 1 goes to this vector. 2 goes right by 2, goes up by 1/2. So this vector. This is the image of 1. What is f of, for example, 2? It is 2 plus 1, which is 3, 2 times 2, which is 4, and 2 squared, which is 4 over 2, that's 2. It's 3 goes right by 4, goes up by 2, it's somewhere here. This is f of 2. So this function sends 0 to this vector, sends 1 to this vector, sends 2 to this vector. So this function, again, sends numbers to vectors in three-dimensional space. So it's a function with values in R3. Now, similar to functions which we had from R to R, here, for the functions from R to R2 or R to R3, we can consider the domain of these functions. So the domain of a function is the set of points which the function is defined there. For example, if as a function from R to R, we consider f of x equal to 1 over x, the domain of f is the set of points where the function f is defined there. Okay. So look at 1 over x. We know we can't divide by 0. So here, x can't be 0. It can be anything but 0. So domain is every real number is possible, minus we can't have 0. So by this we mean all real numbers but 0. This is the domain of f. It means the set of points which f is defined at those points, right? Or for example, if f of x was square root of x, because the square root, well, at least in this course, is defined when the number under the square root is non-negative, so it's either 0 is positive, x here should be non-negative. So for example, here we are assuming square root of -1, well, sorry, it's not defined, yes. So -1 doesn't have square root in real numbers. Not defined over the real numbers. And because in this course, at least here, we are working over real numbers, this thing is not defined for us. So this is defined for us here only if x is positive or 0. In other terms, it's greater or equal than 0. Therefore, the domain of f is the set of numbers which are either positive or 0. So it's from 0 up to plus infinity. And it contains 0, so it's closed at the side of 0. Remember that this set contains 0. It means from 0 to infinity, and it has 0. If we write it like this, it's from 0 to infinity, but does not have 0. It doesn't have 0. These are two different notations, right? So let's let's look at a few examples in higher dimensional case. So for example, when we have a function f from R to R2, like this, suppose f of x is equal to 2x over x squared minus 5x plus 6 and square root of x over 2 minus x. It's a function, f here is a function which takes a number, but its value has two components. This is first component, this is second component. So it's a function with values in R2. We want to find the domain of f. What is the domain of f? When we have these vector valued functions, their domain is the set of points here. We have two components, right? This is the first one. This is the second one. The domain is the set of points where all of the components are defined. In another terms, we should compute the domain of the first one, we should compute the domain of the second one, and we should take intersection of these two answers. So let's do that. So let's write it another time. F of x is 2x over x squared minus 5x plus 6. And the second component is x over 2 minus x. What is the domain of f? Yes, I can go back for a second. Well, there is nothing here. I rewrote what we have here in the next page. Okay. So I want to compute the domain of this function. The idea is that I should compute the domain of this function. I should compute the domain of this function, and then I should take intersection of these two. So let's start with the first function. The idea is that this function is defined, well, the idea is that this function is defined when the denominator is non-zero. So the bad case, the case which the function is not defined, is where the denominator is 0. So whenever you have a fraction like this, and you want to compute the domain, you should look at, here we have 2x, here we have the denominator. You should look at the denominator, and you should say the denominator should be non-zero, because we can't divide by 0. So x squared minus 5x plus 6, this thing, we don't want it to be 0, right? If it's 0, if we divide it by 0, it doesn't have any meaning. So we should find out when this thing becomes 0, and we should remove those points from the domain. The function is not defined if this thing is 0. Okay. On the other hand, this is equal to x minus 2 times x minus 3, which means x is either 2 or x is 3. So at these 2 points, the function is not defined. At these 2 points, if x is 2, this function 2x over x squared minus 5x plus 6, this thing would be equal to 4 over 0. Or if x is 3, this is going to be equal to 6 over 0, right? These things are not defined. So first, we should remove these points from the domain. Okay, that's the first thing. Let's look at the second thing. The second thing is square root of x over 2 minus x. So there are 2 problems here. One is that whenever we have a radical square root of something, what we have under that radical should be non-negative, should be greater or equal than 0, because we have not defined square root of negative numbers. So x over 2 minus x should be greater or equal than 0. The second thing is that here we also have a fraction. So the denominator again should be non-zero. So 2 minus x is not allowed to be 0. Well, When does that happen? That happens when x is equal to 2. So x equals to 2 is not also allowed, which we also had that before. So it's not a new condition. Okay, now we should solve this thing. X over 2 minus x should be non-negative. X over 2 minus x should be positive. Okay, how can I solve this inequality? X over 2 minus x should be non-negative. You see, I have two numbers divided by each other. X divided by 2 minus x. The point is that if both of them are positive, then x over 2 minus x would also will be positive, right? If both of them are negative, then x over 2 minus x is positive. If one of them is positive and the other one is negative, for example, if x is positive and 2 minus x is negative, the result of this fraction is negative. And if x is negative and 2 minus x is positive, the result of this fraction again is negative. These are two cases which we are interested in. And these are the two cases which we are not interested in. Now, there is a way to solve these kind of questions. So I want to find out when x over 2 minus x is greater or equal than 0. Look at the set of real numbers. And look at the roots of these two polynomials. Well, the root of this one is exactly 0. If x is 0, this numerator is 0. For 2 minus x, root is 2. If x is 2, 2 minus x is 0, right? Now let's point them on this real line, 0 and 2. Okay, let's write down our polynomials here. We have x, we have 2 minus x, and then we have x over 2 minus x. Okay? Okay. When here, before 0, x is negative. Well, at 0, of course, x is 0. Between 0 and 2, x is positive. After that, x is also positive, right? What about here? Is 2 minus x positive there or negative when x is less than 0? Here, x is less than 0. What about 2 minus x? Yeah, it's positive. You can always try one number. It's less than 0, for example, minus 1 is here. If x is minus 1, we would get 2 minus minus 1, which is 2 plus 1, which is positive. So here we have a positive number. What about between 0 and 1? Well, for example, 1 is here. 2 minus 1, 1. Yeah, correct. It's positive. Well, at 2, it is 0. After that, it will become negative. Right? What about here? Here, 2 minus x is going to be negative. For example, 3 is here, and 2 minus 3 is minus 1, so it's negative there. Now, if x is, what happens in the first section? Well, if x is negative and 2 minus x is positive, the fraction x over 2 minus x would be negative over positive. It's just like multiplication. Negative times positive is negative. If x is 0, 0 divided by anything is 0. So it would be 0 here. If x is positive and 2 minus x is positive, positive divided by a positive number will be positive. It's just like plus times plus. Positive times positive is positive. If x is 2, 2 minus x will be 0 here. Denominator is not defined. So here it's not defined. And finally, if x is positive and 2 minus x is negative, the ratio is going to be negative. We are interested in the case where this thing is greater or equal than 0. So this is where we are interested in. Where x in this area, as you can see, x is greater or equal than 0. It's less than 2. Right? Okay, let's continue. So our function had 2 parts. It was 2x over x squared minus 5x plus 6. And the second part was x over 2 minus x. The first part tells us domain can be anything, but 2 and 3. 2 and 3 are not allowed because they make the denominator 0. Right? The second part tells us x can be something, well, let's go back. It can be something from 0 to 2. It contains 0. 0 is allowed because 0, well, it would be just 0 over 2 minus 0, which is 0. 2 is not allowed because if we put 2 here, we would get 2 over 2 minus 2, which is 2 over 0, and this is not defined. So it has 0, it's closed, it means 0 is allowed. It does not have 2. So the second part is 0 to 2. And now, because we want both of them to be defined at the same time, the domain is intersection of these two. Okay, so, well, what is the intersection? The intersection will be the set of numbers from 0 to 2. And it shouldn't contain 2 and 3, which it doesn't contain 2 and 3. 2 and 3 are not in this set. So the answer is 0 to 2. And that's the domain of this function. Any question? Okay, let's look at another example. Suppose we have a function from R to R2 where f of x is equal to square root of x squared minus absolute value of x. That's the first part. And that's the first component. And the second component is the square root of log of 5x minus x squared over 4. Find the domain of f. Okay, think about this one for 2 minutes and then we would solve it together. Okay, raise your hand if you have answered or write it in the chat room. Does anyone have the answer for the first part? Okay, what is the answer for the first part? -1 to 1? Okay, that's one answer from -1 to 1. Okay, another answer, r -0 to 1, a different answer. Okay, we have another answer, -infinity to 0 to union union 1 to infinity. All real numbers except 0. Okay, there are a lot of answers. Let's solve it and then we would go back. Let's solve the first part first. -infinity to -1. Yeah, a lot of different composition of 1, -1, infinity to 0. So what do we want for the first part? We have, what do we have? We have squared root, right? We have a radical. What is inside the radical here should be non-negative, either positive or 0, so greater or equal than 0. Greater or equal than 0. So x squared minus absolute value of x should be greater or equal than 0. Okay, so let's write it here. X squared minus absolute value of x should be greater or equal than 0. Usually it's good to consider different cases, right? It's good to say either x is positive or 0 or x is negative. There are two cases. Let's break into two cases. So case number 1, where x is positive or 0. Case number 2, where x is negative. Why am I doing that? Because then we know what is absolute value of x. If x is greater or equal than 0, absolute value of x is equal to x. If x is negative, absolute value of x is minus x. Okay, so let's look at the first case. The first case, the first case is the one where x is greater or equal than 0. Then x squared minus absolute value of x is x squared minus x. We want this thing to be non-negative, positive or 0. That's the word I use. If something is positive or 0, we say it's not negative or it's non-negative. Now, because what we have here is originally is under square root, under radical, it should be non-negative. The point is that I can factor this polynomial. I can write it as x times x minus 1, right? So I can write it as x times x minus 1. I make this table again. X times x minus 1. Okay? Let's look at the roots of these things. The root of the first one is 0. The root of the second one is 1. Let's show them here on this table. 0 and 1. Well, before 0, x is negative. At 0, x is 0. After 0, x is positive. Before 0, x minus 1 will be negative. For example, minus 1 is there. Between 0 and minus 1, x minus 1 is still negative. For example, 1/2 is there, and 1/2 minus 1 would be negative 1/2. At 1, it will be 0. After that, it would be positive. Right? Now, here, what do we get here? We have here negative times negative. Well, negative times negative is positive, so we get positive here. Here, on this line, one of them is 0. 0 times anything will be 0. What about here? Here we have plus times minus. It would be negative. Again, here on the second line, one of them is 0. 0 times anything will be 0, so we get 0 there. What about there? Well, finally there, both of them are positive. Plus times plus is plus. We want this thing to be positive, right? Or 0. So it's either less or equal than 0. So the places we are interested in are this place and this place. So the first one says, this one says x should be less or equal than 0. The second one says x should be greater or equal than 1. But are these two answers acceptable, both of them? Are both of them correct here or not? Yeah, so here I assumed x is greater or equal than 0, right? I'm in the first part. See, I said I'm going to solve this thing in 2 parts. First, I would assume x is greater or equal than 0. Then I would assume x is negative. So I'm in the first part. I'm assuming x is greater or equal than 0. So it's not possible to get x is less or equal than 0 unless x is equal to 0. Because, well, 0 is greater or equal than 0. So the answer here is x either 0 or x is greater or equal than 1. That's the answer for the first part, for this part. Now we should look at the second part. Okay? Now let's consider the part where x is negative. Well, because, you know, x is either, yeah, because the point is that this thing, if it's negative, it's bad. If it's 0, it's okay. And if x is 0, this is 0, this is 0, 0 minus 0 is 0. And square root of 0 is defined. There is nothing wrong about 0. The case we don't like is when this thing becomes negative. So when x is 0, everything's good. So x is in the domain. When the result is negative is the case where we are sad. It's when the function is not defined anymore. Okay, so the second case is where x is negative. We should see what happens.
I have a question.
When x is negative. Yep.
Sorry, in the last slide, why did you put x is less than or equal to 0 or x is greater than 1?
Because this is the answer of this thing. So the point is that we are looking for the points x where this thing is greater or equal than 0, right? You see, my function is this one. My function is the square root of this thing, okay? And I want to see when this thing is defined. Well, if you remember from Calc 1, if this square root is defined when what we have under square root is non-negative. For example, square root of -3 is not defined, but square root of 4 is defined. Okay. Well, tell me, I want to know which part is confusing. So
I got it. I got it. Thank you.
oh, okay then. I shouldn't keep on explaining more.
No, it's okay. It's okay.
Okay. Yeah. Okay. Okay. So the second part is when x is negative. Okay. Well, our function was x squared minus absolute value of x. But when x is negative, absolute value of x would be minus x. So absolute value of x is minus x when x is negative. Therefore, this thing is equal to x squared plus x. X squared plus x can be written as x times x plus 1. Now, again, in our original function, this thing is under radical. So we want this thing to be greater or equal than 0, either 0 or greater than 0. Just like the question you asked. We want this thing to be greater or equal than 0. So we want to find out for what values of x this thing will happen, right? So when is this going to be 0? Well, when x is 0. When this thing is going to be 0, well, this is going to be 0 when x is minus 1. This is going to be 0 when x is 0. We should first find the roots, and then we should form this table. Let's point out these numbers on this table, -1 and 0. And then we would write our factors here. We have x, we have x plus 1, and then we multiply them, x times x plus 1. Maybe I should move this to right a little. -1 and 0. Well, at 0, x is 0. After that, it's positive. Before 0, it's negative. What about x plus 1? At -1, it's 0. After that, it's positive. Before that, it's negative. What about their multiplication? What about here? Well, negative times negative is going to be positive. So here it's positive. Here, when one of them is 0, the multiplication would be 0. So on the first line, we would get 0. What about here? One of them is minus, the other one is plus. Negative times positive is negative. We get negative here. What about here? One of them is 0. 0 times anything is 0. What about here? Well, plus times plus. Positive times positive is positive. Now we are looking for the case where x times x plus 1 is positive. So this is where we are happy. This is where we are sad. This is where we are happy. So for us to be happy, in other words, for the function to be defined, x should be either less or equal than -1, or x should be greater or equal than 0. Well, are both of these things well defined? Do we have both of these things? Are functions defined in both of these cases? Which one is the one which we need? Well, again, look at our assumption. Our assumption is x is negative. We are considering the case where x is negative, right? Because we are saying absolute value of x is minus x. So we are assuming x is negative. So x can't be greater or equal than 0. So this is what we get. X is equal to less. It's less or equal than -1, Okay, let's go back for a second. In the previous part, we showed x is greater or equal than +1, right? Here we are saying x is greater or equal than +1. Here we are saying x is less or equal than -1.
Wait,
What
I'm
does
sorry.
it
Can
mean?
you re-explain why x is greater than or equal to 0 doesn't work?
Here, yeah, because you see, the original function, let's go back for a second. This is the original function. This is what I'm thinking about, right? Square root of x squared minus absolute value of x. Okay. The problem is that when you have absolute value, you can't really work with absolute value. You want to kind of get rid of absolute value. The way to do that is to consider two different cases. Is to say sometimes x is positive or 0, sometimes x is negative. Sometimes x is greater or equal than 0, sometimes x is less than 0. And we break this problem into two smaller, easier problems. We would first solve it in the case where x is greater or equal than 0, because in that case, we can get rid of absolute value. Absolute value would be equal to x. And then we would solve the problem in the case where x is negative, where absolute value is equal to minus x. And we would solve these two problems separately. So first, I solved the case where x is non-negative, so I can write, instead of absolute value, I can just write down x. And then I considered the case where x is negative, which instead of absolute value, I can write minus x. So in the case where you asked, we were solving the second case where x is negative, which instead of absolute value, I can write minus x. So I'm assuming x is negative. Well, how can x be greater than 0 if it's negative? It can't be both greater than 0 and less than 0 at the same time. Does it make sense?
Yeah, thank you.
Yeah, good, okay. So here, what we learned is that x can be greater or equal than 0. What we learned here is x can be less or equal than -1. Well, what do these things mean at the same time? It means x can be less or equal than -1. X should be there, or x should be greater or equal than 1. So here, what we get is that from -infinity to -1 is an x is part of the domain, and sorry, or is union. X should be greater than 1. So these are two sets which we can define it. Now there is just one other case. Yeah, thank you for reminding me. And that's 0. If x is 0, this thing is also defined. So this is what we have here is the domain of x squared minus absolute value of x. It means if x is somewhere here or somewhere here, or it's 0, the function is well defined. There is nothing wrong with that. So the domain of this function is the union of these three sets. Well, but it's not over. We have not solved the problem yet. What was the problem? The problem was a vector valued function. It has a second part. We should compute the domain of the second function too. Right now, we only computed the domain of the first function. Now we should compute the domain of the second function. Now we should compute the domain of the second component, which is the square root of log of 5x minus x squared over 4. Well, there are two kinds of difficulties here. One is that when we have square root, when we have radical, whatever is under the radical should be non-negative. So here it can't be negative. What we have here can't be negative. On the other hand, when we have log, this thing which we have in front of log, that number should be also positive. So here we can only have positive numbers. So there are two things we should check. One, because log of 5x minus x squared over 4 is under the radical, this has to be non-negative, greater or equal than 0, 2. Because 5x minus x squared over 4, we are taking log of that. This should be positive itself. If we have these two properties, then the function is well defined. Then it makes sense. So we should compute these two things, and then we should take intersection of the results. Okay, you can do that. Think for a few minutes, and then we solve it together again.
I have a question, sorry. Can you re-explain the first part? You said 5x minus x squared over 4 must be positive because it's under a square root, but then how about the log has to be positive itself, right?
Yes.
Okay.
Positive or 0, you see? When you say positive, it means it can't be 0. 0 is not positive in, like 0 is not positive. When you say it should be positive, it means you are ignoring that it can be also 0. Okay, so that's why I usually don't say positive, I say non-negative. But yeah, you're basically right. Because it's under the radical, it can't be negative. So it should be greater or equal than 0. Yeah, but the second problem comes from the fact that we don't have log of negative numbers. We don't have log of -1. This is not defined, right? So what we have here should be also, it should be positive. So we have two restrictions. We should think about these two at the same time. Does anyone have the answer? No, these parts are not going to be on the midterm. Actually, they might help you. With these things might help you, but they wouldn't be explicitly on the midterm. Yeah, that's correct. Okay, yeah, these answers are pretty close. Let's see. Let's try the first thing. We should, well, the vector valued functions are on the midterm, that is true. And the limit and derivative will be on the midterm. I might not ask about domain explicitly, but you should know about that. Okay, so yeah, the vector valued functions are in the midterm. But I said I wouldn't ask you about things which I just talk about them today, which means I'm not going to test you on the domain of vector valued functions. But anyway, you should know that. Okay, so let's start with the first one. The first thing. So we want to see when log of 5x minus x squared over 4 is greater or equal than 0. Okay, so the point is that 0 itself equals log of something. What is that? 0 is log of, does anyone remember? Yes, that is correct. 0 is log of 1. So here, instead of 0, I can write log of 1. Log of 1. So it means log of 5x minus x squared over 4 is greater or equal than log of 1. Now, no matter what is the base, it's e or it's 10. When the base is greater than 1 itself, when the base, this is the base. When it's greater than 1, if log of a is greater than log of b, it would imply a is greater than b. When base is greater than 1 itself. So that's the case here. E is 2 point something and also 10. Both of them are greater than 1. So it doesn't matter which one you assume. Because log of 5x minus x squared over 4 is greater or equal than log of 1, it means 5x minus x squared over 4 is greater or equal than 1 itself. We can kind of cancel these logs, right? We multiply both sides by 4, we get 5x minus x squared is greater or equal than 4. If I take everything to the right-hand side, I would get x squared minus 5x plus 4 should be less or equal than 0. I would get to this inequality. Is there any question up to here? X squared minus 5x plus 4 should be less or equal than 0. So we use this fact. In base 10 or in base e, if log of a is greater than log of b, it means a is greater than b itself. Here we have log of 5x minus x squared over 4 is greater than equal than log of 1. It means 5x minus x squared over 4 itself is greater or equal than 1. Well, might be, but let's practice. We are kind of practicing, but you are right, yes. So what we want here is for this polynomial to be non-positive. So x squared minus 5x plus 4 should be less or equal than 0. We would follow the same technique. I would first decompose this polynomial. What are the roots of this polynomial? So first I want to write this polynomial as multiplication of two linear factors. What are the roots of this polynomial? How can I find them? X minus 1 times x minus 4. And then I would form the table I mentioned before. We have, well, the root of this one is 1, the root of this one is 4. I would mention 1 and 4 here. We have x minus 1. We have x minus 4. We have x minus 1 times x minus 4. At x minus 1, at 1, x minus 1 is 0. Before that, it's negative. After that, it's positive. Well, what about x minus 4 here? Well, we can try. 0 is there. 0 minus 4 is negative. So it's negative here. What about here? Well, 2 is there, 2 minus 4, minus 2, it's negative there. It's 0 here, 4 minus 4 is 0. Here is positive, 5 minus 4 is 1. 5 is in that area. What about their multiplication? What about this one? Well, here we have negative times negative, it's positive. Here, one of them is 0, the multiplication would be 0. Here, one of them is positive, the other one is negative, the answer would be negative. Here, one of them is 0, the multiplication would be 0. Here, one of them is positive, one of them is negative, the multiplication would be negative. We are interested in the case where this multiplication is less or equal than 0. So either negative or 0. So this is the part we like. This is the part we don't like. So we like it when x is greater or equal than 1. We like it from here to infinity. Oh, sorry, I made a mistake in the last one. You're right. Both of them are plus, their multiplication would be plus. So we like only this part. We don't like this part either. So it would be greater. So the part we are interested in is from 1 to 4. Does it contain 1 and 4? Yes, because if x is 1 or if x is 4, the result would be 0. The square root of 0 is defined. So the answer is from 1 to 4. Okay, so that's the answer for the first part. This part says from 1 to 4. What about the second part? The second part says our polynomial should be positive. In other words, 5x minus x squared, well, we can multiply both sides by 4, should be greater than 0. I can write it as x times 5 minus x should be positive. The root of this one is 0, the root of this one is 5. Yes, your answers are correct. I can form the same table. 0 here, 5 here. I have x, I have 5 minus x, and I have x times 5 minus x. Well, here x is 0. Before that, it's negative. After that, it's positive. 5 minus x is 0 at here. What about before that? For example, in this area, when x is 1, well, 5 minus 1 is 4. It's positive here. It's positive also here. But it's negative there. So after 5, for example, if you try 6, it would be 5 minus 6 would be negative 1. It's negative. What about their multiplication? Well, what about here? We have minus and plus. Their multiplication would be negative. Here, one of them is 0. The multiplication would be 0. Here, both of them are positive. The multiplication is positive. Here, one of them is 0. The result is 0. Here, one of them is positive. The other one is negative. The multiplication would be negative. I'm interested in the case where the result is positive, not even 0. Note that even 0 is not good because this thing, what we have here, we are taking its log and it can't be 0. Log of 0 is not defined. What we have inside log should be a strictly positive. So the case we like is exactly this case where x is between 0 and 5, but it doesn't contain 0 and 5. Okay. So we have two answers. One of them says between 1 and 4. The other one says between 0 and 5. These things should be correct at the same time. So we should have both of them. X should satisfy both of these properties at the same time. X should be between 1 and 4, and X should be in 0 and 5. So let's look at the real line. 0, 1, 4, 5. X should be in this area, and X should be also in this area. But it should be in these two areas at the same time, which simply means X should be in this area. Again, the intersection of these two sets is, if you take intersection, we get 1 and 4. So this is the domain of the second component. Now let's go back. Let's look at the, no, that's not the original function. Let's look at the original function. This is the original function, right? Let me get rid of these extra things. That was our vector valued function. This vector valued function itself contains two parts. We computed the domain of each part. What was the domain of the first part? We spent a good amount of time to find the domain of the first part. What was the domain of first part? Well, we found it here, -infinity to -1, union 1 to infinity, union 0. So this here says -infinity to -1, union 1 to infinity, union 0. Let me show it on the set, on the real line. This is real line, right? This is -1, this is 0, this is 1. So the domain would be from -infinity up to -1. It doesn't contain -1. It contains 0. It does not contain 1. Goes from 1 to infinity. The domain of the second part, yes, was from 1 to 4. So the second part says only the numbers from 1 to 4 are acceptable. Now we should take intersection of these two sets, because F is defined if first component and the second component, both of them are defined. So we should take the intersection of these two things we computed. Well, what is the intersection? If you look, it would start at 1, the intersection starts at 1 and goes to 4. Well, does it contain 1? Well, this one contains 1, but this one on the left side, it doesn't contain 1. If 1 is not in this green set, it wouldn't be in the intersection. So the final answer does not contain 1. What about 4? Well, 4 is here, also 4 is here. So it's in both of them, it will be in the intersection. The final result, the domain of this function f, is the set 1 to 4. Any question?
The u, the like after negative infinity.
No, that's union.
Comma -1. That means or, right?
Yeah, that union. Well, union means it's either in the first set or in the second set. Yes.
Okay.
So maybe it's a good thing you mentioned. Maybe some students, well, haven't seen this thing before. If you have two sets, A and B, this is, we read it as A union B. It means if something is here, it means it's either here or here. This thing means A, we read it as A intersection B. If something is here, it's in A, and also at the same time it's in B. And then there is a way to see that if this is the set A, set of some elements, and this is a set B, set of some other elements, A union B, it means something is either in A or in B. So it can be anywhere. It's in their union. So A union B, we can think about it like that. What about A intersection B? it means A is here, B is here. If something is an intersection, it means it's in A and it's in B at the same time. Well, these are the elements, the things which are in A and B at the same time. This is a schematic picture. It's not something in R. It's just a schematic, conceptual picture.
Okay, and also I think that it includes 1. Unless I wrote it down incorrectly, we had it including 1 in the first part.
Ah, okay, let me go and check. Here? Oh yeah, yeah, you're right. I copied the answer incorrectly. It does have 1, so I was wrong. It has 1 and minus 1. Thank you. But well, then it means 1 is here and 1. So 1 is on the left set and 1 is on in the right set at the same time. So it is in the intersection. This notation matters again for people who might not have seen this notation. If I write something like this, it means the set of numbers from 1 to 2, which has 1 and 2. This means the set of numbers from 1 to 2, which it does not have 1. 1 is not in this set, but 2 is in this set. This means the set of numbers from 1 to 2, which it has 1, but it doesn't have 2. And this means the set of numbers from 1 to 2, it doesn't have 1, it doesn't have 2. Okay. Any question here? Anything else we should discuss? Everything's good? Okay. Let's solve one final question, this time a 3-dimensional example. Suppose we have a function f from R to R3. The values of this function is in R3. It has 3 components. Suppose f of x is equal to, it should have 3 parts. Okay, say the first part is log of x minus 2. Well, I'm not sure how hard it's going to be. Let's try it. In base x, suppose the first one is log of x minus 2 in base x, the first component. The second component, let's say it's square root of log of 9 minus x squared. This time, let's say it's in base 1 over 2. The base is less than 1. It is important. And in order to just make something as challenging as possible, because it's Calc 3 and you should see challenging things, let's say the third component is log in base 3 of log in base 2 of log in base 3 of log in base 2 of x. This is our function. And the question is finding the domain of f. Now it has 3 parts. We should find the domain of the first function. We should find the domain of the second component. We should find the domain of third component. We should take intersection between these 3 functions. And then that would be the final answer. So start with the first one. Start with the domain. Find the domain of log of x minus 2 in base x. What is that? Does anyone know what are the rules here? Well, I told you what we have here should be positive. We can only take log of positive numbers. What about the base? What are the, do we have log in any base? Exactly. So base, there is a rule about log. Base should be positive and base can't be 1. So there are 3 things. This guy, x minus 2, should be positive. Base should be positive. Base can't be 1. write down these three things and see what we are going to get. Okay, think for a few minutes and the answer. So let's see, here there are a few things we should have. X minus 2 should be positive. We can take log of positive numbers. Base must be positive. Base can't be 1. Here the base is x itself. Well, the first rule says, the first thing says x should be greater than 2. The second one says x should be greater than 0. The third one says x shouldn't be 1. We must have these restrictions at the same time. Well, what is the intersection of all of these things? X should be greater than 2, x should be positive. Well, of course, x should be greater than 2. X can't be equal to 1. Well, it wouldn't be if it's greater than 2. So the answer for the first function is x should be greater than 2. And we can write it as interval from 2. It can go to infinity. It's anything greater than 2. And it doesn't contain 2. Because if x is 2, x minus 2 would be 0, and log of 0 does not make sense. So that's the first part. This is the answer for the first component. Let's look at the second component. Let's erase here. Okay. So what about the second component? It's log of 9 minus square root of log of 9 minus x squared in mod 1 over 2. Okay, what are the things, what are the rules here? This thing should be positive. It's under radical, so it should be positive. Right? We are taking its square root. Well, what we have here, 9 minus x squared, we are taking its log. So 9 minus x squared itself should be positive. So we have these two things. We should compute each of them, and then we should take intersection. Yeah, this is non-negative. Thank you. That is true. So because log of 9 minus x squared is under the radical, it should be non-negative, so greater or equal than 0. And then 9 minus x squared, because we're taking its log, it should be absolutely positive, strictly positive. So we should compute these two. Okay, think about these two for a few minutes. Okay, let me explain this. So there is a general rule which is important. I told you, if we have log of A greater than log of B, what does it imply? Well, it's important what is the base. Say the base is B. There are two cases. Either B is greater than 1 or B is less than 1. And these two cases are different. If B is greater than 1, log of A greater than log of B means A is greater than B. If B is less than 1, actually it means A is less than B. Log would change the direction if B is less than 1. So some of you didn't consider that. Here, base is 1 over 2. It's less than 1. So the second case applies. Okay, let me compute it completely then. So there are two things here. We should consider both of these equations. One is log of 9 minus x squared in base 1 over 2. The other one, 9 minus x squared itself. So this thing should be greater or equal than 0, but 0 is log of 1 in base 1 over 2. So log of 1 in any base is 0. Doesn't matter what is the base. Log of 1 in any base 0. So whenever we see 0 in these inequalities, we can write log of 1 in the base which we are talking about. Doesn't matter what is the base. Okay? So we can cancel log, but because the base is less than 1, the direction of this inequality will change. This is what we are going to get. So 9 minus x squared would be less or equal than 1. We can take x squared to the other side and 1 to the other side. 9 minus 1 would be less or equal than x squared. It means 8 would be less or equal than x squared. Okay, what does it mean? X squared is greater or equal than 8. What does it mean about x? Yeah, I wouldn't touch the equality. If we have the equality, if I change like the direction of the inequality, this equality will stay. Okay, so it means x squared minus 8 is greater or equal than 0. Can I decompose this? Can I decompose this polynomial? Well, I can. It would be x squared minus square root of 8, x squared plus square root of 8. Oh, sorry. X minus the square root of 8 and x plus the square root of 8. That's the decomposition of this thing. Remember, in general, x minus a times x plus a is x squared minus a squared. Here, a squared is 8, so a would be square root of 8. So does this decomposition make sense for everyone? Should we continue or there is confusion? So x squared minus 8 can be written as x minus the square root of 8 times x plus square root of 8. This thing should be positive. Again, we can form our table. The root of this thing is the square root of 8. The root of this one is minus the square root of 8. So we have these numbers, minus the square root of 8 and plus square root of 8. Then we have x minus the square root of 8, x plus the square root of 8, and their multiplication, which is just x squared minus 8. Okay, x minus the square root of 8 would be 0 here when x is equal to square root of 8. After that, it will be positive. After that, it will be, positive. Before that, it will be negative. X plus the square root of 8 would be 0 at minus square root of 8. After that, it will be positive. Before that, it will be negative. What about their multiplication? Well, minus times minus is plus. It would be positive here. 0 times anything is 0. Plus times minus is negative. 0 times anything is 0. Plus times plus is plus. We want this thing to be non-negative. So the good cases are this case and this case. So it means what we like here is the case where x is greater or equal than square root of 8 and x is less or equal than minus the square root of 8. We like it when x is greater or equal than square root of 8, or when x is less or equal than minus square root of 8. So that's the answer to one piece of this question. Do you have any question here? If no, let's continue with the other part. The other part was, because we are taking log of 9 minus x squared, whenever we are taking log of something, whatever we have should be positive. So 9 minus x squared should be positive, which means 9 should be greater or equal than x squared. Okay, so you can do these computations pretty fast if you are familiar with these things. If you are not really familiar, you should follow these steps I'm telling you. If you are good with computations, you really don't need to do all these computations. Probably you can answer these questions instantly. But if you are not very good with computations, you should follow these steps. Okay, I don't need to do that. So 9 minus x squared, this thing can be written as 3 minus x times 3 plus x. It means what we have here is positive. Well, root of the first one is 3. The root of the second one is minus 3. So I have minus 3, and then I have 3. What are my polynomials? I have 3 minus x. I have 3 plus x. And I have their multiplication, which is just 9 minus x squared. When x is 3, the first polynomial is 0. What about after that? Well, for example, 4 is here, right? 4 comes after 3. 3 minus 4 is negative. So our polynomial is going to be negative here. What about before that? For example, 2 is here. 3 minus 2 is positive. It's going to be positive here. Our second polynomial is going to be 0 when x is minus 3. What about after that? Well, 0 is there. 3 plus 0 is 3. That's positive. It's going to be positive there. What about before that? Well, minus 4 is here. 3 plus minus 4 is minus 1. It's negative. What about their multiplication? Well, plus times minus is negative. Positive times positive is positive. Negative times positive is negative. On these lines, we have 0 because one of them is 0. We like the case where our answer is positive is exactly here, where x is between -3 and +3. Or in the language of intervals, it would be from -3 to +3. Okay, so this is the answer we get here. Remember that we had another condition too. The other condition was this thing. X should be greater or equal than square root of 8, or x should be less or equal than square root of 8. We should have these two restrictions at the same time. So x should be greater or equal than square root of 8, or x should be less or equal than minus the square root of 8. That's one of them. And at the same time, x should be between -3 and, oops, sorry, -3 and 3. It means we should take intersection, and means intersection. So the first one says, look at square root of 8, look at minus the square root of 8. X can be here on these red parts. Okay, well, first of all, where is 3? Is 3 here or it's here? Is it before square root of 8 or after square root of 8? Yeah, it's on the right side of the square root of 8. So 3 is there, -3 is here. The second condition says x should be in this interval. Well, we should take intersection. And as you can see, the intersection is from here to here, this part, and then here to here. That's the intersection, right? So it starts at -3. It goes to minus the square root of 8. X should be there, or x should be from square root of 8 and goes to 3. Okay. Do we have these numbers or not? Well, x can't be equal to 3, so we don't have, or -3, so we don't have -3. X can be equal to square root of 8, so we have a square root of 8, minus square root of 8. Again, we have a square root of 8, but we don't have 3. So this is the final answer for this part. Okay. let's go back to the original question. The original question, we can ignore the negative part because of the log results. Yeah, so let's go back to the original question. Let's see. Up to this point, we computed the domains of the first and second functions. The first one told us x should be from 2 to plus infinity, x should be here. The second part tells us x should be from -3 to minus the square root of 8, or from square root of 8 to 3. That's the first thing. That's the result for the second part. Now we should look for the domain of the third function, the last part. Okay, do you want to think about that, or you want me to solve this thing instantly too? Do you want to think about it, or you want me to write down the answer? Okay, you can think about it for 2 minutes. Good. That's better. That is correct. Okay, here we have log in base 3 of log in base 2 of log 3 of log in base 2 of x. Okay, so we know whenever we are taking log of something, that thing should be positive. We are taking log of this thing, the whole thing. We are taking the log of the whole thing, right? We're taking the log of that. So that should be positive. So the whole red box here should be positive. What is that? Log of 2 of log of in base 3 of log in base 2 of x. That thing should be positive. But what is 0? 0 is log of 1 in any base we want. Since here I have base 2, I would write here in base 2. So we can cancel log from both sides. I can cancel this log with this log. Okay. It means log in base 3 of log in base 2 of x, if I cancel these logs, should be greater than 1. Okay, but what is 1? So let me go to the next page. Maybe, I'm not sure if you all can see the bottom of the page here. So let me write down one more time. So the question is log in base 3 of log in base 2 of log in base 3 of log in base 2 of x. We want to find its domain. Because we are taking the log of the red box should be positive. So log in base 2 of a log in base 3 of log in base 2 of x should be positive. But 0 is log of 1 in any base. Here, because I'm the most outer log has base 2, I would write the base 2 here. And then I can cancel these two logs. So log in base 3 of log in base 2 of x should be greater than 1. But there is another way of writing 1. Can anyone tell me what is the better way of writing 1 here in this inequality? No. So yeah, that is true. So log of any number in its own base is 1. So log of 2 in base 2 is 1. Log of 3 in base 3 is 1. Log of 1 over 2 in base 1 over 2 is 1. This is an important fact. So here I can write 1 as log of 3 in base 3. Because log of anything in its own base is 1. Okay? So log in base, if I do that, it means the left side, which is log in base 3 of log in base 2 of x, is greater than log of 3 in base 3. And then I can cancel log in base 3 with log in base 3. What I would get is log of x in base 2 is greater than 3. Okay, here I have log in base 3. I want to have log in base, sorry, here I have log in base 2. I would like to have log in base 2 in the right side too. What should be the number here? What is the number which its log in base 2 is 3? Well, you should remember the definition of log. It's 2 to the power 3. So I would write this other fact here if you don't remember it. Log, say, of 2 to the power n in base 2 is n. It's just this power. So log of 2 to the power 3 in base 2 is just this number 3. Well, if I summarize these, log of x in power 2 should be greater than log of 2 cubed in power 2. I can cancel this log in base 2. It means x should be greater than 2 cubed, which is just 8. That's the answer to the final part of this question. Is there any question? Do you all remember about log, or you've already forgotten everything? Okay, now let's go back to, yeah, if you've forgotten about log, I can send you a short note about log, so you can review. It might be also important for the exam because these are from Calc 1, Calc 2, these are prerequisites. So you might need to review these. I would send you something to review. Anyway, so the first part, the last part says, it's quite interesting. The last part says x should be greater than 8. So it would be from 8 to infinity. Okay, so we have computed the domain of each component, and now we should take intersection of these things. We should take intersection of these different domains. What is the intersection of all of these things? Can anyone tell me? So let's look at let's use different numbers. Let's use blue for this one. Let's use green for this one. Well, and red for the last one. So we have this set of real numbers. The first one says it should be from the domain should be from 2 to infinity. So the first one says the domain should be here. The second one says it should be from -3 to minus the square root of 8, or from 3 to square root of 8. Oops, sorry, I made that's yeah. One of them is closed, one of them is open. This is open, this is closed. Or it's from 3 to square root of 8. And that's the other way. It should be here. The last one, the red one, says it should be from 8. Well, we should continue. This line. The last one says it should be from 8 to infinity. It should be in the domain. Any point x should be in the green area, and it should be in the blue area, and it should be in the red area. What is the intersection of red, green, and blue? Nothing. So it's the empty set. So the domain of this function is the set, empty set. There is no point which this function is defined for that x. There is no x, none, which this function is defined there. So the domain of the function is the empty set. This is the notation for the empty set. It means no point x. None. Okay, and that would be the end of this subsection about the domain of the vector valued functions.
Just to clarify, is this going to show up on the midterm or is it going to be on the final?
Final.
Okay. And is it going to be like this level of difficulty, or is it going to be one of the first problems we had? Like, will you give us something with like the log 3, log 2, or no?
Well, actually, this is not very difficult. And at some point, you should review log because, you know, in the chapter 3 and 4, if say we have 4 chapters, if we get towards the end of the book, we need to use these properties pretty heavily. So we really need to know these things. So I would, if you don't remember about log or trigonometric functions or log, I would really like you to review. I really prefer. One thing I might do is once I can, well, after the midterm, I can give you a set of notes for these things, and I can set your homework from these things. So you would review these things pretty well. I might not give you something as complicated as the ones I just solved, because it might take so much time, and in the exam you might be stressed, and you know, I think it might not be the best thing to do in the exam, but I like you to know how to do this thing, even if I'm not going to give it to you in the exam. Okay? Okay then. Yeah, everything we learn up until the end of Tuesday is on the exam. Okay, so that would be the end of the domain. Let's have 10 minutes break. Let's continue at 11 and 10. We would continue with vector valued functions and similar things.